Welcome to Chapter 4, where we will be talking about linear regression and correlation. Specifically, we will be doing what's called simple linear regression. It's called simple because it's the fewest number of variables you can use and still perform a linear regression. Everything that you can do beyond that usually has a different name. It's either called general linear regression or multiple linear regression. But don't let the name simple fool you. This can be a complicated process. The first thing we're going to look at is what is called association, and that's trying to describe the relationship between two quantitative variables. The first way we're going to do this is very visual in nature, so we're going to perform visual techniques to decide if these two are related. So below I have a graph of what's called a scatter plot, and scatter plots are unique in the fact that everything we've done up to this point has been one variable. A scatter plot is of two variables, two quantitative ones to be specific. So when you look at any given point on the graph, this represents two variable values for a single individual. So be thinking when you see points, it's actually two values, one individual. Be careful, because this is different from everything else we've experienced so far. There are four ways we're going to look at trying to describe association with. And the specific first one we are going to be starting with is what's called direction. We call the direction negative if it has a general pattern running from the upper left to the lower right, or positive if it's going from the lower left to the upper right. This is a general pattern. This is not going to be perfect in most cases. Real world data very rarely looks very clean, just so you're aware. The other thing is, if you're thinking, oh, this sounds kind of like slope, that's exactly the kind of behavior we're describing. Is it increasing and increasing or decreasing and decreasing? The other thing to keep in mind as you look at this is we also are thinking about how or another way to interpret it rather, is that when you think about negative, we're really describing a negative relationship. So we also learned back in the day that negative can be thought of as opposite, and that's how I want you to think of this. My behavior of my variables is opposite of each other as I think about them. So if you're trying to think of an example of this, a negative one would be like, oh, car age and value of the car. So as the age increases, as I get an older and older car, the value decreases. They're doing the opposite of each other. When one increases, the other decreases, and so on and so forth. If you're behaving oppositely, that's a negative relationship. So as far as positive, if you're trying to think of how this would go, my variables behave the same way, or they do the same thing. So you could think about number of units you sell and profit you make. Clearly, if you sell more units, you'll be making more profit. If you sell fewer units, you'll be, making less profit. They're doing the same thing. They're either both increasing or both decreasing, and that's a positive relationship. The next thing we look at is what's called form. You can also think of this as shape if you're a little uncomfortable with that word. And it's the overall pattern we see in the data or relationship that we're looking for. So what we want to look for is something that looks fairly much like a straight line or looks kind of linear, hence the name line. It has the word line in it, Look right there, there's the word line for linear. You get the idea. Basically, if it's not a line, we're not interested in it. So if it's not like a line, we call it nonlinear. So basically anything that doesn't look straight. If it's got any type of curvature, something kind of rounding to it, like a wave pattern, anything that's not straight, we are going to call nonlinear. Or nonlinear. Woohoo! So this is a little bit harder to see because not all data looks very clean and straight and perfect. Keep in mind as you look at this that you should just look for general form. Does it have any curvature to it or not, is what I'm really asking. The third feature that we're going to be looking at is what's called strength. Strength is probably the more difficult one to judge, and really what we're talking about here is the strength of scatter. How much scatter is it? I'm hoping you're looking at the yellow boxes in each of these slides and noticing that's like the short version of these. So if it's very tightly clustered and your shape is really, really strong and it's pretty clear what's going on, like you could almost play connect the dots with it with a single line, then you probably have something strong. If you've got a little bit of scatter away from that, we usually call it moderate. And if it's, you know, we kind of see a pattern and like I can almost see a shape, we usually call that a weak. And then if you almost see no pattern whatsoever, we say that this has no association because it just looks like some sneeze or something. It doesn't look like there's any shape whatsoever. So strength you should think about as deviation away from this shape. It's how much spread I am away from the shape. The last thing we're going to look at is what are called outliers. I'm sure that you've heard of these before because you talk about them in Chapter 3 and Stat 1. And it's basically the idea of something that doesn't fit the pattern. It's the one that seems to not match anyone else. If we were still talking about the car example, it would probably be something that maintained its value because it was classic or something like that. It was already aged to the point where its value couldn't decrease, and so therefore its value was starting to increase because it was a rare vehicle, would be an example of an outlier, or an older vehicle. You know what a classic car is, I hope. If not, don't worry about it. Let's look at a specific example. So one of the things that the Texas Transportation Institute does every year is they look at traffic congestion and the cost by freeway speed. So when I say cost here, the cost of congestion, it's looking at how much money is wasted by the fact that the cars aren't moving. So gas expenditure, wear and tear on the roadway, stuff like that. Roadways were meant to be driven on, not sat on. Lost because wages, because people ended up not making it to work on time, things like that. So what's interesting about this is they list the cost per person per year and then the peak period freeway speed. So you should be thinking about those four aspects as you look at this graph and trying to describe them at this point. So be thinking strength, direction, shape, outliers. Do you see any? Let's see if we can answer that question. Okay, so this looks negative because it starts at the upper left and goes to the lower right. And it looks fairly linear. It's got some spread away from linear that's not very, very, very strong, or it's not very, very spread out. So I would call this strong because it's easy to see the shape. And then you might tend to think that this might have some outliers. Specifically, I'm talking about if you were looking at these 2 points and thinking, oh, well, they're a little bit off by themselves. They're not that far away from the rest of the data to where I would consider them to be an outlier, and the same thing here. So if you ever run into this problem where you're not sure something is an outlier or not, just remember to yourself, it probably has to be something that's like so off pattern that it's not near anyone else, either vertically or horizontally. So in particular, this value has some points that are nearby it horizontally, not necessarily vertically. They're far apart vertically. If you had something that was like way the hell down here, like here, that's a point. Let's see. Okay, it's too big for the rest of them. But if you had something down there like that, I would be like, okay, yes, I agree with you. That's an outlier. Or even if it was just like just far enough over here in this corner, I would consider that an outlier as well. It has to be off pattern. And if you have something that has a lot of scatter, you usually don't have outliers just because everything's so scattered out that, you know, your pattern contains a lot of things that are far away from each other. Okay, let's look at the data on the mean age of cyclists killed each year. So I'm hoping you notice that you look at this and you see, oh, as the age increases, so does the mean age. I wonder if there's something going on here. Is there a relationship? Let's make a scatter plot and then describe it. So here's the graph of that data. I don't know about you, but this is looking pretty good. Not that death is a good thing because, one of the problems here is it's very easy to acquire dead people data. So yeah, this is a much stronger linear relationship with absolutely no questionable outliers, and it's positive. As the year increases, the mean age of the death is increasing as well. And this is a very strong one. Like, I don't even like to use the word very, and I would totally use the word very for this one. Okay. One of the most important things when it comes to assigning rules in your scatter plot is deciding who depends on who. I'm hoping you notice that all scatter plots have an X and a Y axis, and I'm hoping you remember that X and Y variables are something you learned about in algebra, and you use them to describe relationships, particularly the Y we usually call the dependent, and the X we usually call the independent. And we'd say things like, oh, Y depends on X. And we want to label these clearly with scale and numbers because we want to do a good graph, and with units and everything like that. But we also want to be clear about which variable goes where. In thinking about our previous example about mean age of cyclists, it makes more sense to say that the mean age of death of cyclists depends on the year than to say the year depends on the mean age of cyclists. That seems super weird. I'm not going to be able to predict the year by knowing the age. And if you're not sure, you can back up and look at the data and remind yourself that the mean age 36 occurs multiple times and in different places, and therefore makes it difficult to tell what year it is. That lack of uniqueness tells you that the dependence goes the other way. Also, and the other way doesn't make any sense. Anyway. So we're going to use that to try to make predictions. We think there's a dependence, we think there's a relationship. How can we describe this? So as we look at each scatter plot, we have specific X and Y values making up the coordinates. These coordinates make up our relationship that we are attempting to measure here. What else do I want to say about this? I probably should pause it right now, but I'm not gonna. Oh, and remember, as you look at each of these X and Y values, they represent a single individual. In statistics, we have one variable that's playing the role of explanatory or predictor. It's the one we're using to predict the other value. And the other variable is the response, the action or output or response that we're looking to predict. So as you look at this, I want you to be aware that these words are different from what you're used to using in algebra. Think explanatory is X and response is Y. So I'm looking to take my X and use it to predict what's going on with Y, or I want to use my X to explain the response I see in Y. And usually only one of these relationships makes sense, just like with the cyclists and the mean age of death. Usually, in simple linear regression, we use the word explanatory. In multiple, we tend to use the word predictor just because there are many predictors. I'm not sure why that difference was made, but at the same time, just so you know, we kind of use both of these words interchangeably. They mean the same thing, so that's okay. But, you know, just because you see the word predictor, don't freak out. It's just a fancy word for the X one. It's also alphabetical, if that helps you. Like, explanatory and predictor come first in the alphabet, and so does X. Anyway. So we always place our explanatory on the X, and we always have our response as the Y. And these behave the same way as the independent-dependent relationship that you're used to in algebra. So let's look at the mean age of cyclists again, because I'm really overusing this example. Hey, does it make sense on who I plotted where? I hope so, because if you look at the mean age, trying to use it to predict the year is a little bit weird. However, if you're trying to say, oh, well, what's the mean age of the cyclist? And someone told you the year, you could be like, oh, 2001, 36. But if I told you, hey, the mean age is 36, you'd be like, what year is it? Who knows? That one's kind of hard. And that's usually true. Usually trying to use one to predict the other makes more sense than the other direction. And that's an easy way to tell which variable is which. Who can I use to predict the response? So herein, I'm kind of done describing this visually. We're now going to move forth into trying to describe this numerically. This is a common theme in statistics. I have a graphical visual way. I know how to think about this. Now let's build a numerical way to do it. I did not know this slide was here. All right, so when two quantitative variables have a linear association, we want to be able to describe how strong is that, and that's where we need a numerical value. The one that we are going to be using is called the correlation coefficient, and we use the word R for correlation coefficient. and it's a cross product. If you don't know what cross product is, don't worry about it. Basically, we're looking at the z-scores for each x and y for a single point, producting them, and then averaging them. So if you need a way to think about this, remember z-scores are about how far you are from the mean. So I look at, for any given point, how far it is from average in both directions, in x and y, and then I product that. The reason why you're doing a product there is because you want to make sure that you account for both over and under estimates. So if your y happened to be like lower and your x happened to be higher, one would be positive and one would be negative, and you want to make sure that overall you're seeing the big picture there, so you'd end up with a negative value. The other thing about this is it's all about telling you how far away from average am I, and then averaging that. So it's kind of interesting what correlation does. And specifically, it takes you away from a medial line, what the means are in both directions in x and y. So one caution about correlation is that it's used to measure the strength of linear association between two variables, and only linear. The number one mistake I see students make with this is they'll try to use it to measure association on anything, not just the linear guy. So, and I'm going to warn you right here, right now, even though I'm going to talk about conditions and that's what I'm supposed to be doing, you got to know this, okay? Your calculator is dumb, Minitab is dumb, computers are dumb. Well, okay, they're not all dumb. They can't tell when you shouldn't do this, okay? So if you've got a graph of something that definitely has a curve in it, you can still calculate correlation on it, even though it only measures the linear one. The result you will get will be useless, but you can still do it. So I'm going to write this. All machines will still calculate this. For nonlinear stuff. And this is the most important thing, the result is useless. Man, this makes my handwriting terrible. What do I want you to get from this? You are better than a machine, okay? You can look at a scatter plot and tell me immediately, oh, that's got a curve in it. I shouldn't be using correlation because it's not linear. Okay. A machine will look at a scatter plot and be like, it's a scatter plot. I can't tell if this has a curve in it. And if you don't believe me, they've tried using facial recognition software to do this. It never recognizes a curve, or even just a pattern that looks different than a line. And so the problem with this is you got to be the one to decide, is there a linear association? Should I use correlation to see how strong it is? It's up to you. We're all counting on you. So that's when you should. Here's where you can. If you're dealing with quantitative variables, okay, let's be honest with you. If you're dealing with categorical to measure relationships, you should be using not correlation, because this one needs two numbers to be able to do it. You should make sure it's linear. I've already said this once, but hey, make sure it's linear. The last thing is make sure you don't have any outliers, because unusual values or outliers tend to pull correlation towards it and therefore will skew your values away from being linear. So be careful. It actually makes your correlation weaker if you have an outlier every single time. So usually we don't want to do correlation when we have an outlier. Doesn't mean you can't, we just don't want to. All right, here's what the correlation looks like. So the sign of correlation gives you direction. So if it's negative, you're dealing with a negative direction. If it's positive, you're dealing with a positive direction. Correlation is firmly between 1 and -1. This is one of the ways you're going to be able to tell if you got something incorrect. If you got a correlation of 3, you know you're doing the wrong thing. It's bigger than 1. Yay! Anything bigger than that is incredibly unusual. And if you're, I'll get into that in a minute. Since we're dealing with z-scores, this treats x and y symmetrically. It can't tell who should be your x and who should be your y. If you accidentally have them backwards, it's not able to tell the difference. You still get the same correlation. And the last thing to keep in mind is correlation has no units. That's because it uses z-scores. Z-scores are distances, but in particular, they're how many units you are away from the mean. It's like, you know, if you're shoe size was 4 inches, which makes no sense, the z-score for that would be 4, no inches involved. It has no units. So correlation, since it uses z-scores, also has no units. Whee! Okay, couple things to keep in mind. Since correlation uses z-scores, it doesn't care about scale. So if you just suddenly decide all of your measurements in inches need to be in centimeters, your correlation still stays the same. It doesn't care about scale. If you pick everything up and move it over, it comes up with the same correlation because it's measuring the relationship between your two variables, not where they're located at and not how big they are. Okay. But it's also sensitive to outliers. So if you suddenly throw a giant into your data, things are all going to go to crap. So a couple other things I want you to keep in mind as you look at this. I'm going to draw you a little number line. Well, it's straighter than I've done in a while. So I'm going to put -1 here, 0 here, and then 1 over here. All right, so I'm going to tell you how we think about these when it comes to their correlation value. If you get a -1, that's what's called a perfect negative. If you get a +1, that's also called a perfect. My F did not come out, I'm sorry. But it's the +1. And that means you have a perfect straight line. You're literally, all of your data lies on your line. It's where everything falls in between that things get a little screwy. Okay, so if you're at 0, there's no association. You're not related at all. So the idea as you look at this is, well, you want to have some relationship. If you get close to 0, that's bad. So further from 0, better. Positive and negative tell you direction. Okay, so if you fall in the -0.3 to +0.3 range, these are generally what we call the weak values. There's not much going on here. That's very good, and you probably should scrap and try again because you got nothing useful. Okay. If you fall between 0.3 and 0.7, either in the negative or the positive direction, you're in the kind of meh, it's okay. It's not a great model. It's not doing a fantastic job. You don't have a hugely strong relationship here. If all you're looking to do is to use this to do some basic calculations and just do a little bit of work, and you don't need absolutely perfect numbers and nobody's life depends on it, you can go with a model that's in that range. It doesn't matter so much. What we want to get, though, is the stuff that's left over. You want to be in, oh, I'm like out of colors. Let's use purple. This is the it's doing a good job range. If you're above 0.7, that's a really strong association. And I wrote meh. I wrote good. I should have written strong. And that's what we want to see. We want a strong relationship. Because then I can do something with that. I can work with that. So there's a little scale to help you judge how good of a job your correlation is doing, or not how good your correlation is, that's so messed up, how strong your relationship is between your two variables. How associated are they? Because that's what it measures linearly. Let's look at a correlation table. Okay, so this is a correlation table. I'm going to show you how to read this. I'm hoping you notice there's some 1s on the diagonal. 1 is perfect. Well, why is it perfect? Because as you look at the 1s, so for instance, let's do, come on, let's do this one right here in the middle there. Well, I mean, that's not really in the middle, top corner. This is the strength of the linear relationship between the pages variable, number of pages, and the number of pages. Huh? Yeah, that's right. You're relating it to itself. Of course it's going to be perfect. That's why we have 1s on the diagonal. The other thing is most statistical software nowadays won't even report the diagonal because it's kind of silly as you're looking at this now, right? It's just a little bit, like off board. So next, take a look at the rest of the values in here and ask yourself, ooh, where's the weakest relationship? Okay, that's enough time. Right here. This is the one that's closest to 0, width with number of pages. And at first when I saw this, I was like, what do you mean width and number of pages for a book? Oh, these are books, by the way. Yeah. Shouldn't the width of a book be related to its number of pages? Be careful, you just made the mistake I did originally too. It's not the thickness of a book or how, like, measuring the book along where the binding and all the pages are in between it and then the other binding. So I'm saying that width is actually like the length of your cover of the book, not how far it is from cover page to cover, which is super weird. That's actually thickness, so it makes sense. I mean, I've seen books that have weird dimensions. Most of them are around like 8.5 by 11, but some of them are super weird and have like 10 by 10 and other strange things. And photography books are like that too, where they have really, really strange dimensions where things will be longer and shorter. And it makes sense that width is not related to your number of pages then. Think about children's books. Some of them are really, really wide because they need to have big pictures on them for children to see, and lots of colors and entertaining things on them, and big letters so they can read them and learn to read. And it has nothing to do with the number of pages. So of course those aren't correlated to each other. Okay, well that was the weakest. Where's the strongest? Right below it. Ah, thickness. Now, thickness is related to number of pages. That makes tons of sense. Because when you think about the number of pages in the book, every page you add should be adding to your thickness a little bit. These should be highly correlated with each other. Aha! You have figured this out. Okay, so that's your strongest relationship present. The other thing to note is this upper triangle has nothing in it because this is symmetric, which means looking at thickness versus number of pages is the same as looking at thickness with number of pages. So, you know, what's the point in it all? It's the same number, so why repeat yourself? All right. Here's something you need to look out for. Lurking variables are a difficult thing. Sometimes the relationship that you're seeing between your variables is caused actually by somebody who's in between them, a third variable, lurking around and actually affecting both of them. So what might be happening is you're like, oh, I got X and I want to relate it to Y, but really there's this third guy out there, Z, who's related to both of them. And it's this relationship, the one between Z and the other two, that's making this one look so strong when it might not actually be that strong. It's actually something else that you should be measuring. Lurking variables are difficult to spot. If you ever end up working with a data team on a project, this is why it's very important you have somebody on your team who is very familiar with the data, who's been working there a long time. Usually the easiest way to spot a lurker is to have somebody who has more experience with the data. The more experienced a person is with the data, the more likely they are to be able to spot a lurker, a certain other cause other than what you're already observing within your data. Let's look at an example of a lurker to kind of help you out with this. And they're hard to spot. So don't think that, like, you know, everybody in the world should magically know what this is and you're the only one who has a hard time with it, because, like, usually everybody does. So in this example, we're going to look at life expectancy, average age of men and women in years, versus the number of doctors per person for 40 different countries. If you look below at the scatter plot, it has some issues. It's not perfectly linear in shape, but its scatter is not huge, so it's a strong relationship, and it just barely gets into the strong category when you look at its correlation because it's got a little bit of nonlinearness to it. But as you look at this relationship, it's a strong relationship. It's positive, it's linear. It looks like these two variables are related. It appears that doctors per person is positively related to life expectancy, which means that as you look at this, you suspect that I should, in order to make people have a longer life expectancy, I should have more doctors. So that means when you look at certain third world countries, if you want to help them out, you should just throw doctors their way. That'll help, right? Or do you think there's something else going on? If you're immediately thinking, oh, I think there's other problems that third world countries have that might affect their life expectancy besides the presence of doctors, and see if you can come up with one thing that would do that. Ready? Take a minute to think, maybe pause the video, or, you know, you can just go ahead and, you know, listen to what I'm going to say next. Ready? Here's the thing. In a lot of developing countries, the higher the standards of living are, the more likely you are to live longer. So another one I would say for this would be access to clean water. That always will preclude a higher standard of living and therefore increase your life expectancy rather than doctors. So keep in mind that the next time you encounter something like this, just because it looks like there's a relationship doesn't mean there couldn't be something else involved. And resist the temptation to call them causation, because, well, anytime somebody takes regression and says one thing causes the other, they've misused statistics and they've lied horribly. Do not say that regression or correlation indicates cause. All right, let's look at the cycling example again. So an insurance company analyst suggests the idea that the data ages of the cyclists' accidental deaths are actually due to the entire population of cyclists getting older. Huh? And not to change the safety riding habits of older cyclists. What? This seems already crazy, right? So, what would we call the mean age of cyclists if we had that variable available? Well, it would be the lurker. So as you look at this, if the entire age of cyclists kept getting older and older, so if you looked at the population of people who are riding bicycles in general kept getting older, we would say that that was more the cause than anything else, and therefore it would be the lurker that was hiding in the background and causing the average age or mean age of cyclist accidents to increase. It wouldn't actually just be that these two were related to each other. Welcome to the linear model. Below I have a scatter plot of Amazon's book prices versus weights. I gathered this data in 2015. It was late 2014. Nope. No, it was 2015. It was January. Sorry. And as you look at the model, I'm hoping you notice that it has a general positive trend. It looks kind of linear, but it has a lot of scatter. So it looks to be like a moderate relationship, not necessarily a weak, because you can still see the shape. But it isn't strong. And I listed the R value for you here, which reflects that as well. It's only about 0.498. Let's see if we can build a relationship around this, or a model. So what we want to do is we want to come up with a line equation relating price and weight that describes this relationship specifically. And the idea is that it's a scatter plot with a lot of scatter to it. So not all of these points are going to be fitting with that line. How can we do the best job possible to make sure that we try to do the best for all these points as we can? We need the residual. So we don't know we know the model's not gonna be perfect. That's just something we gotta accept. If not, you're not sure, go back like 3 slides and look at that graph. There's just no way. So no matter what line we draw, it's not gonna go through all the points. So what we wanna do is we wanna try to find the best line we can. And the residuals are something that's gonna help us do that. So if we take a linear model of a line, and so this is the equation we're going to be using, y hat, that stands for predicted y. Oops. With intercept b0 and slope b1, this is the equation of line we'll get. So this is the predictions that we're getting if we use the line. And then the residual error, also known as just the residual, or the little e, is the difference between your actual value and the prediction you made. So think of this as this is the one from the actual data. And then y hat is the predicted value. So this is predicted from the line. In that sense, the residual error is a true error. It's how far your prediction was off from the truth. So as you look at this, there's a reason why we use the hat on top of the y's, and that's because we already have something named y. That's the data. The hat is meant to represent the part that you're making. And this is something that has always been true in statistics. We use the little lines and bars and stuff on x's and y's to represent means. It's something I constructed, not the actual residual raw data. And so whenever you look at this, you should think, oh, the hat means I made this, I constructed this. And we can use residual to see a couple different things. In particular, if the residual is negative, that means that I over-predicted because the thing that's being subtracted must be the larger one. And if E is positive, then I underestimated because the thing that was the actual value was the larger, and so my subtraction yields something positive. So how are we going to use this? We're going to use it to make the line of best fit. So the line of best fit, or least squared regression line, is designed to make the residuals over all possible values be the smallest they possibly can. This is a minimal optimization problem. It's difficult and revolves a little bit of calculus, but it turns out that this always has the same result, and it always yields the same line. That's why I got a name, because it's always the same dude. Yay! Okay, so we're going to write our equation of the line as y hat equals b0 plus b1 over x. This is going to be our line on the scatter plot. And remember, it's not going to hit every single line, every single value on the model, but it's going to do the best job we can. And as a reminder, the hat is for the approximate or predicted value. Let's look at my Amazon data as an example of this. So the line of best fit for the Amazon data, oh, this little box is showing up, that should be a hat. It says that the predicted price would be 10.35 plus 0.477 weight. So as you look at the slope of this, that means that for every ounce of weight I add to my book, my price goes up by about 0.477, or about $48. Sorry, 48 cents. Ah! Yay! So what you've learned from this is it's okay to be wordy if you can sell your book, because the heavier the book is, the more money you'll make, right? Right. Craziness. Let's look at what the intercept means. So the intercept is 1035, but keep in mind intercepts are points, so they have two components to them. It's 1035 for price when the x variable is 0, so when weight is 0, for weight 0. So that means when your book weighs nothing, it costs $10.35. Huh? So a book that doesn't exist costs $10.35. A book that's in your mind that you're thinking of. I'm being sarcastic, I'm sorry. This makes no sense, and this frequently happens. Sometimes your intercept means absolutely nothing to this equation, but your slope will always mean something. So how do we find slope? Ha 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 ha. So traditionally when you've found slope in the past, you would have done the following. In case you forgot, the old symbol for slope is m1. We're not using that. And that would be your change in y over your change in x. That doesn't look like a 2. There we go. Oh no, wait, that's a 1. 1. Got to keep this right. 2. There we go. All right. Whew. Couple things. Here's how we'll be calculating slope now, because we have way too many points to be using this one. But they're spiritually the exact same thing. Okay, more than spiritually. They're the same idea, but with statistical applications. So what is this? Well, there's the standard deviation of y, so spread of y over spread of x. Oh, okay. So, change in y, spread of y. Change in x, spread of x. And then we've got correlation factored in here. So it's not just how far they're spread, but it's also how strongly are they related to each other. Suddenly this makes a lot of sense for your slope. And in particular, if they have a negative relationship, you're going to end up with a negative slope because of the correlation. And if they have a positive relationship, you end up with a positive slope because of the correlation. This is much stronger. Lastly, we should always make sure that the means are accounted for. Your average value is going to be a point that your line will always go through, because you want to be able to relate them at least on average, since we're using standard deviations and z-scores to calculate all of this, and therefore we use it to find b0, the intercept value. So you start out by plugging in the means, and then you take this and you solve for b1, and that will yield you b0, and that will yield you the following equation. So that's how you find the intercept. All right. So we can also use the equation now to find a residual. I'm very angry that my hats didn't show up. So I took a book that previously has been used in the Innovation Marketing Management class, Peter Drucker's book, Innovation and Entrepreneurship. And in 2015, when I looked up its price on Amazon, I also was able to record its weight, which means I can use my price weight value association and linear regression line of best fit to predict what the price would be of Peter's book. I really shouldn't call him Peter, I don't know him. So since I know the weight, I plug that in for the weight variable in my equation. I multiply these two together, and then I add 1035, and that comes up with $13.40. $13.40. That's what my equation predicts the price of the book will be. So the actual list price for the book, when I looked it up, when I was looking up the weight of the book, was $16.99. So I can actually calculate the residual for this book specifically and see how good my line did for just one prediction. So my residual error, or E, is I take the $16.99 that the actual price is and subtract the predicted price of $13.40, and it's $3.59. And before I started recording this, I actually went and checked, and my line is doing a better job right now than it had been when I first looked and made these slides. So, you know, I got better over time. Woot woot. The other thing to notice about this is positive, which means that my line was an underestimate. If you're having a problem with the idea of positive, shouldn't that be over? Nope, it's under, because I'm reevaluating the line, and the line produced that value, which is smaller compared to the actual value. That's why it's under. Okay, so when can you do a regression line? When can you make these? Well, unsurprisingly, since the regression used correlation, we need the conditions of correlation to be true. I have to be using something quantitative, it has to be linear, and there needs to be no outliers. That's when you should be doing the regression line. Cool. Let's do another example using summarized data. So if you know the mean, the standard deviations, and the correlation, you can actually calculate the line this way as well. So this is the summary statistics from the cyclist data from was it the first example? No, the second example we had. So here's how you do this. You always start with slope. Woohoo! So the first thing we're going to calculate is B1. So we find correlation and my two standard deviations, and I plug those into the formula, and I calculate that, and I came out with 0.8. And then I'm going to use that in calculating the intercept. So I now have the intercept set up, and then I'm going to plug in my two means, those guys right up here. And then I calculate that, and it comes out as negative, which I'm hoping you look at that and you recognize that that's a little bit of a crazy value. It's one that doesn't make a whole lot of sense realistically, but that's okay. We're going to use it anyway. And then the last thing you want to do is you want to make your equation. And I would caution you that as you're doing your homework and such, don't skip this last step. You've done all the work to come up with the slope and the intercept. Don't skip making the line. I would also say make sure you use the names of the variables, not general x's and y's, because this is way more meaningful than it is like x and y are this line and things. No. We have context with our numbers. That's mean age and that's year. We should use those contexts to our advantage. Here's another way you can use correlation. Since slope is a fixed value and doesn't change, you can use it to investigate the relationships between values that are certain numbers of standard deviations away from each other. So for instance, if you know when you look at the standardized values for the x and y with their z-scores, they're one standard deviation away from the mean, you can plug those values in and notice that your slope is just the correlation, which is interesting. So as you picture moving away from the mean of your graph, which would be the center of it, where your mean for x and mean for y meet, As you move one standard deviation in each direction, you'll move one correlation in the other direction. So I'm thinking about this as r over 1. A little strange, but it works. Similarly, you can use the formula for intercept to rewrite it as well. So if you are no standard deviations away from the mean, aka you are at the mean exactly, you actually get zeros in here, and therefore you have no intercept. So anytime you standardize anything, the regression equation formula will simplify into being, oh, well, what is this related by? Well, you know, zy is just r times zx. And I'm using zy and zx here because I'm not using x and y anymore. I'm standardizing, so I'm using the standardized version, which is literally what's on my next slide, so I don't know why I just did that. Anyway, so if you're using standardized values, you notice that, oh, how are the z-scores related? Well, when you look at the equation of the line and use linear regression, they're related by just the correlation for the standardized values. So how can we use this? Well, you can look at what's going to happen when I move 1 or 2 standard deviations above the mean in one variable and say how the other will react. It gives you a percentage of movement. So for instance, if you look at the Amazon book data, we know the correlation to be 0.498, and we can actually express that relationship using the previous equation. And then we can say that, oh, so if the mean of a book is 1 standard deviation heavier, the mean book is then going to have about 0.49 more in its cost, or about half the cost, because this is kind of close to 0.5 of the previous book, which is interesting, I think. Their relationship is rather strange. It increases by 50% in costs. Alrighty. The big thing that this tells us is if I'm 2 away, then, you know, it's only going to be 1 standard deviation bigger. So think back to the Amazon line. It was z equals zy, sorry, equals about 0.5. I'm super rounding here just so you can see what this relationship looks like. So that's saying that if I move 2 away in the x direction, this would be 0.5 times 2. Then that would only be 1 away. And that means that as I move farther away from the mean, my regression effect reduces this. So if you think about it that way, the closer to the mean you are, the more accurate your line is going to be, and the closer your values for x and y are going to be together. And this is called regression to the mean. So now that we know how to make the model and to look at a little bit about the things that we can use it for, we should be able to ask ourselves, is it a good model? This section is dedicated to, did it do a good enough job? How can I tell? And you shouldn't be too surprised that we're going to approach this like we have everything before it. Let's look at a visual thing, and then let's look at some numbers. So these are the 4 things you really should be checking when it comes to assumptions and reasonable content for your linear model. Is it quantitative data? Does it look linear? Are there no outliers? And does it have equal spread? AKA, does my model seem to do a good job everywhere, not just for certain values? In order to do that, we look at a residual plot and ask, does it have equal scatter for all x values? So a while ago back, when I was looking at Peter Drucker's book, I did a single residual for you. I'm hoping in your heart of hearts you had this instinctual fit of, really, she's only going to check one value to see if this is good, and shouldn't she be checking more than one value? And that's exactly what a residual plot is for. It checks multiple values to see, does my model do a good job overall, not just for a single value or a couple values. And I like the equal spread to check. It really does see, am I doing a good job overall? So when you approach model making, what you should be doing is taking your data, looking at your predicted and your residual, and asking, oh, you know, is this doing a good enough job? So you should be looking at how far is my data from the predicted values. And we're going to be looking for, does this make sense? So ideally what we want to see is nothing interesting. This is the exact opposite of a scatter plot. We want to see on a residual nothing interesting. I want to see patterns, I don't want to see reduction, I don't want to see shape. This is one we should want to see to look like a sneeze petri dish, like somebody just splattered things everywhere, you know, like paint. there should be nothing interesting happening. So I don't want to see outliers or clusters or any type of shape whatsoever. And particularly, I'm going to talk to you about what shapes are bad shapes as well, and when we have a good residual. Whee! So here's the residual for the Amazon book prices. This is a good one. Ah, happy times in residual land. Did you think it was a good one? Because if you're thinking, oh, scatter plot, I need to have shape, it needs to be strong, it needs to be linear. Completely different type of graph. This is a residual. This is the one where we want to see nothing going on. I want no patterns, no interesting features, and it's good. This is the kind of thing you want to see. This is the kind of thing you don't want to see, because I'm hoping you immediately notice, this has a pattern. Do you see the big horseshoe? Oh, it's not quite a U, but, you know, it's a little lumpy. This has a shape. That's bad. This has a pattern. It's curved. This is a very bad residual. It's nonlinear. And it has a distinct curve. In Stats 2, when we look at multiple linear regression, we are also going to talk about how to fix a curve pattern like this to make it not be a problem, which is kind of nice. But you still need to check your residuals to be able to tell if it's even there before you can fix it. So, you know, there's that to look forward to. So the last thing I want to tell you about is how you can numerically measure it. And I'll warn you right now, this is not the best way to do this. There will be other values we use, so this is just one of their tools. So we use the standard deviation of the residuals, or the spread of errors. So you see down here, it's like spread error, SE. Just so you're warned, Minitab just calls this sucker X. Sorry, not X, S. I need to pronounce better. Just an S, and it's a capital S. And that's what most statistical software calls it as well. So there's actually a whole branch of statistical software named after it. It's just called S. There's another one called R. People are having a good time with naming stuff in simple yet confusing ways. So as you look at this, I'm hoping you notice that it's literally a standard deviation. There's the square root, there's the square, and there's the averaging across things. Remember, E is your residual. Whee! In case you forgot, because we just learned about what he is. So what we want to see is we want this to be small. When it's small, that means you probably have obeyed equal spread in a good way, because if you have a couple errors that are large, this actually blows up really quickly. Want this to be small. And here's where we have a little bit of a problem. Small is relative to the current size of your data. So if you're trying to predict something in millions of dollars and your standard deviation of residuals is like 1,000, that's good because you're not off by that much on average. And that's a good thing. But some people might look at this and be like, oh, 1,000, that's a big number, that's bad. And it's relative to the size of your data, because another person might be working with, I don't know, widths of engine parts, in which case, you know, maybe they need something that's in a couple centimeters, in which case, if you had something even like your standard error being like 1 centimeter, that's huge when you're dealing with tiny, tiny pieces, and that would be bad. So it's relative to the size of your data, so be careful. When I say small, you shouldn't be thinking, oh, I want this close to 0. It matters how big your data looks too. So, you know, keep in mind this is relative to size. And that's the only thing I don't like about S. Because if you're dealing with like prices of home sales and you're off by only a couple $1,000, you should be super happy with yourself. You did a pretty good job. You know, these are difficult to judge. Let's look at another terrible graph. So here we have another residual, which I warned you already is bad. Oh no, more bad graph. And I'm hoping you're looking at this and thinking, what's so bad about it? It's a little bit harder to spot on this one, but you notice how it's real like close and narrow here, and then, oh my god, what happens over time? Oh my gosh, this is getting bigger and bigger and bigger. This is what we call a fan shape. Fan shapes are bad. fact, they're the worst one, and they're the one to look out for the most. That means that your model did a really good job here. And then that was supposed to be good. Looks like God. I'm sorry. And then over time, or as your values increase, it got worse. Usually this is a sign that you need a multilinear model of some sort, or you're missing something. Usually it means that you need another variable in there somewhere that's accounting for this change over time, or change over units, or change over fitted values, whatever they happen to be. They might not be time, is what I'm trying to say. So keep that in mind. So as you look at this, oh my gosh, it appears that it's getting worse over time. It has a shape. It's a shape you haven't seen before, but it does happen. It also can go the other way too, where it starts out terrible and gets better. That means your model is doing better in recent times and worse earlier. That might not be a bad thing as much though, because if you're looking to predict only recent values, then it does a fantastic job and you shouldn't care. Here's the cyclist data. Are you at all surprised by this one? I hope you are, because I look at it and I see some huge issues. One, it has an outlier right there in its residual. That's bad. The other thing is it has a sort of distinct dual shape to it. I see almost a multilinear model for this, where it needs to have two lines. Poop. This is not such a good thing. In fact, the scatter plot here is showing you that, oh, you also possibly could have seen, oh, this looks like an arc if I ignored the outlier. Either way, I'm hoping you to see that this has some distinct shapeliness to it that it should not have. This means that your model actually did kind of a terrible job. So here's me repeating myself. Hey, there's definitely a pattern. And I have an outlier. Oh no, bad things. Okay. So, unfortunately, I warned you about S. It's size dependent. That's bad. Let's look at the other thing we can use to judge our model that's not so size dependent. And that's R squared. And yes, that's definitely what it is. It's just, I'm going to take little r and square it. So in case the capital R confuses you, this thing has a couple different names. It's also called big R squared. And it's all about the variation of the residuals, which is an interesting idea. What did I want to say about this? This also has a couple other names, just in case you run across these. One of the other names for this is the coefficient of determination. This name is not used as much as it used to be, so just so you know. Or if you end up reading something that has that word in it, you'll have some exposure to it. And it's also called the ratio of variation. We're going to use that one a little bit more. My terrible math joke about this is, what a difference a square makes! Okay. So R, as you remember, is between -1 and 1. So when I square that, I get stuff that's always positive. So you kind of fold the number line on top of itself, and you can go from 0 to 1. That's what's right there. So again, if your correlation were 0, you're predicting nothing. This isn't doing a good job. If it's closer to 1, you're doing a great job, and you're predicting almost everything. Let's see how that works. Here's the pages, number of pages versus thickness. I'm hoping you notice that this has a very strong linear relationship. Well, it's not very strong. It's got some scatter to it. It doesn't look like it has any outliers. If you're questioning these guys, they're on pattern if I had more data continuing this. Sorry, it just occurred to me you can't see my mouse. If you're worried about these two as being outliers, these are on pattern if this continued forward. It's just that I don't have a lot of data over here in this area. So those are not considered outliers for that reason, just so you're clear. So what we want to do is we want to ask ourselves, how thick of a book is, how thickness of a book is related to number of pages. Wow, sorry. And we want to be certain that the book with more pages is actually thicker. And how are these two related? And there's our scatter plot. Scatter plot looks pretty good, so it's pretty reasonable to continue doing this and finding a linear model for this data. So let's make a model. Here's the equation. I used Minitab to do this one because I was feeling kind of lazy. I didn't do it by hand, so there you go. As you look at this, your intercept is kind of interesting in this case because it tells you, hey, my book has no pages and it's 0.28 in thickness in inches. What? So one of the ways you can interpret this is, oh, is that the covers of our book? Sure it is. That could be what's causing that. And that's kind of nice because it's like, oh, that kind of makes sense. On average, when I look at the thicknesses of books, the covers are about 0.28 inches. If you want, you can go around with a ruler in your house and figure that out for yourself. Some are thicker than others. This is an average, though, so be careful. The other thing to note is that, oh, there's my slope. So that's how thick one page is, because for every page I add to the book, that's how much I will add in thickness. So we think that 0.0189 is the thickness of a page. So there's an interpretation of slope and intercept for you off of this model. Okay, last but not leastly, we note that the correlation is 0.822, and we had noted that this was pretty strong in general in the first place. What I'm going to show you next is a little bit of an interpretation of where R squared comes from, and it'll help you make sense of what this is used for. So I have two box plots here, one of which is the residual of the textbook example I just did, and one is just of the thickness variable, so the response variable I'm looking at. And I'm looking at this and saying, oh, so residual is how much is left over, how much I wasn't able to account for. How much did I miss? And you can kind of look at these and line up certain parts, like line up your medians, and then notice I wasn't able to get about this much of that first percentage right there, and I wasn't able to get this much, so that much is not accounted for. And I got a little bit up here that I missed too, so you know, I missed that much, and I missed this much, and then you're like, you gotta do this, and then you're like, I missed that much. What percent did I miss? So of the parts I scribbled out in red compared to the blue total, how much did I miss? What percent would you give that? And like, I don't know, maybe somewhere between like 50%. It looks like it's slightly smaller than half. It might be a little bit bigger than half too, because it's kind of hard to tell with this graph, but you're just trying to do the best you can. And I'm going to say like, I don't know, 60%? Maybe. I'm looking at how much was accounted for here. So how much was not missed or how much wasn't residualed. So we're actually in the middle of constructing a way to tell this. How good did our model do, and how much of it ended up being perfect, and how much of it ended up being useless, which is hard to judge, but it turns out, yes, you can do this. You can use you have something that will develop and be able to judge your model, and that's exactly what R squared is for. So really, R squared gives us, and I'm going to underline this as I speak because this is the most important part, so watch where I'm going with this, or I'm going to highlight it. R squared gives us really the fraction of the data's variation accounted for by the model. How much did the model explain? So earlier I was drawing all over and scribbling the red stuff out. That was the stuff that was left over. So R is the opposite of that. It's the stuff that the model explained, residuals the amount that it wasn't able to explain. AKA 1 minus R is the fraction of the original variation left from the residuals, the stuff it wasn't able to explain. Yep. Usually when we do this, we report it as a percentage. Ooh, I'm still on the highlighter. I'm so sorry. That looks like terror disaster time. We report, oh, come on, R squared as a percent. And yes, I'm going to physically do one in a second. So, well, literally the next slide. Ready? So if this looks like crazy nonsense time, here's the specifics behind this. Okay, R squared, Amazon thickness model. Ready? So there's my R value, and I'm just squaring it, and that's the number you get. I was pretty close with my 60. Ooh, that's magic. Okay, so we would say that about 67.6% of the variation in thickness is accounted for by the number of pages. That's it. And about 32.4% of the variability in thickness has been left by the residuals, or not accounted for by your model. So my model was able to account for 67.6% of what was going on. That's not great. It's okay. It's not miraculous. but probably there's something else going on there too, like quality of paper or region of distribution, or maybe even just who the printer was would be a better indicator here. So if you're looking at this and thinking, maybe I can do better than 67.6% if I throw in another variable, congratulations, that's the more complicated version of linear regression, trying to include enough variables to account for more of the variation that you're seeing in that variable. Okay, so how big should R squared be in order for you to decide it's good? This is kind of like the number scale I was doing before. So now we're going to go from 0 to 1. So this is standing in for 100%, obviously. Most scientific people want you to be, above 80, honestly. And if you're doing non-scientific stuff, you're okay if you're usually between that's way too close to 80, 0.5 and 0.3. And if you're in this range, nobody accepts you, which is sad. And this is I like to call this mathematical limbo, because the people that fall in there, they're like, oh no, I gotta either improve my model or change how I'm doing things so that this works and is acceptable. I like limbo. I think it's funny. If you ever run across somebody who comes up with a 100% model, this is the sign that you know that they flubbed their data. They have messed with it in some way to make it perfect. This is suspicious. Okay? The other thing that we're going to see, or that you'll see in your future maybe, is that if somebody's really, really close to 100%, they're probably overfitting their model. They're probably using way more than they actually need and overpredicting. And usually overpredictive models are only good for a certain range of values. So there's something to watch out for in your future. Should you run into somebody who's like, nah, my R-square is 99%, I'm good. No, they're not good. They've overfitted. In fact, they've probably done a bad job. Let's look at an example. Oh no, the cyclist data again. Yay! Okay, so the R value for the cyclist data is actually 0.96. So let's look at what the R squared is going to tell us. The R squared, if you square 0.96, is 0.92, and that tells us that 92% of the variation in the mean age of cyclist deaths can be accounted for by the trend of increasing age over time. So, mean age of death is caused by time. 92%. That's pretty darn good. Not good enough to be suspicious, but pretty darn good. Okay, if you're thinking, okay, so I can predict anything with this. Let's do a little bit of reality check. Okay, just because you get a result doesn't mean it should be a good thing. Okay, don't deal with things that fly in the force of common sense. One of the videos I'm going to post below is about how causation and correlation are not the same thing, and that's a mistake that a lot of people make. If you make that mistake, you'll be saying things like, oh, I can make more Nicolas Cage films by drowning people. And if that sounds extreme, yes, it's crazy. The next thing you should ask yourself is the slope reasonable? And the reason you should ask this is because slope always has an interpretive and factual meaning that is helpful. So if your slope is telling you nothing, you should be highly suspicious of your results. The next thing you should ask is, does your direction seem right? Think back to my example with cars, with age and price. If you were seeing that as the car aged, the price went up, you should be highly suspicious of that. That doesn't seem right. If it flies in the face of your common sense, you should question your results and wonder if something was done incorrectly. And that's literally what I said. I'm hoping statistics teaches you a healthy dose of skepticism, because if it hasn't yet, it totally should. Okay. There's a couple underlining relationships that can go along with linearity versus nonlinearity. These next few slides are not necessary for Stat 1. If you are in Stat 1, you can go ahead and skip the next few and not pay too much attention. Nonlinearity is something to watch out for in Stat 2. Woohoo! So, the following below, it has a very different shape from what you're used to, because this is clearly nonlinear. If you're looking at this, it has a curve. It also curves only to one side. This is what is known as an exponential regression, and so we would actually need to use a nonlinear model to model this. One of the ways that you can do this in a way that will give you a linear model is that you can do a transformation to make it be linear. Okay, so as you look at this, you might think to yourself, oh no, this is exponential or quadratic in shape. What can I do? Well, one of the things you can do is you can take the response variable and do the opposite operation to it, so not an exponential, but a log, and then fit a linear model to it. So this approach doesn't come up that often, but it does show up occasionally. So what you would do is you would do a logarithm. Come on, pen. It's not going to let me write this. You would do the log of cell phone and then map your data to a linear regression using HDI versus cell phone. Yep. Because a logarithm is the opposite of an exponential. Another thing you might want to consider doing is using a different correlation value. So there's something out there called the Spearman rank coefficient, and what you can use it for is to take something that looks like it has a slight curve to it. So this definitely has some sort of curviness to it, but it's hard to tell what degree of curvature. So you might ask yourself, is it a cube? Is it quadratic? Is it linear? Is it nonlinear? Is it logistic? Is it exponential? And the Spearman rank will actually rank the data instead of their value and help you decide which one you should be using. So for instance, the Spearman rank correlation for this is 0.89, nope, I can't read, 0.876. And so that would tell you that the degree is of relationship between the two variables is actually a linear relationship. Interestingly enough, I would not have predicted for that for these two. So there you go. All right. Here's a third approach for you. So this is doing the log that I mentioned earlier. So I take the cell phone data and I log it and graph it against HDI. And what that allows you to do is notice this now looks linear, and then you can do the linear regression between these two variables, log of cell phone and HDI, and get a result. And then if you need to take that result and bring it back to the original data, you can do the exponential to return yourself to the original shape and size of the previous value with a linear regression. So we have to express and then re-express and undo things to be able to do nonlinear regression. We're going to do some examples with this in the example videos for the Stat 2 students. Again, if you're in Stat 1, you don't need any of this. We're not doing it. So what can go wrong? Don't confuse correlation with association. This happens all the time. Correlation is a specific number to describe association or relationship. Association is the four specific parts of strength, direction, shape, form, we also called that, and then outliers we see in a scatter plot. Those are not the same thing. Don't try to correlate things that are categorical. I'm sorry that I'm laughing at that one, but you literally can't do it. Make sure you're dealing with linear, otherwise that's not something we're interested in doing this semester. Sorry, not this semester. This class. Look out for outliers. Don't mistake correlation for causation. That's the one that will get you in tons of troubles. And watch out for lurkers. They're hard to spot, but I believe in you. Yeah, you got a chance there. You guys are brand new. You're more creative than I am. You have a chance of spotting lurkers. Don't fit a straight line to a nonlinear relationship, aka don't try to put round pegs in square holes. Watch out for extraordinary points, aka outliers, because they will skew your data unmercilessly, and don't extrapolate far beyond the data. So extrapolate means to pull out points beyond your data. So when I say beyond your data, I mean that if your data is from the 90s, you probably shouldn't be using it for the early 2000s or like the 1950s. Those time periods are nowhere near each other. Same principle with any other data piece. If you're going beyond what your data values actually has, you're probably going to get something crappy. Anyway, remember the linear model is just trying to summarize the relationship between the range of x values that you have. And Minitab does this as well. It only produces your line for the parts that it's good for. Anyway, don't choose your model on R² alone. You should also use S, and you should look at its slope and decide if that's reasonable and informative. Otherwise, you're just ignoring half of what you know. So, what have we learned? Hey, look at a scatter plot and look at its 4 pieces. Direction, form, strength, and whether or not there's an outlier to decide whether or not you have a linear association or nonlinear association. Make sure that when you're analyzing R, you can summarize it in terms of what it's telling you, not just in strength, but in direction. So, there's that. And make sure you're not saying that these two cause each other. What else? When you're modeling a line of best fit, it's never going to pass through all the points. It's trying to do the best it can for all values present, which means if you have a lot of scatter, it's never going to be perfect. And even then, if you just have a little scatter, you're probably not going to as well. Remember, slope tells us you change in units y per x, and that's always informative. Intercept, not so much. We use r squared to tell us how good of a job our model did or how much variation did it account for the y variable in terms of x. Yay! Recognize that regression has the mean in it. You know what I mean? Make sure you use residuals to assess the quality of your model and how good it did, and watch out for equal spread.